All right, we're working toward talking about non-equivalent resonance structures, but first we need to recall how to do formal charges. And the formal charge is the charge on an atom in a molecule or polyatomic ion. It's the charge in the Lewis structure. Formal charges should add to the overall charge for an ion or should add to zero for a neutral compound like water. To do the formal charge, it's going to be the group number. So this is the number of valence electrons that we're assigning based on the periodic table, minus the number of lone pairs. And then this minus gets conducted here, minus half of the bonding electrons. The group number gives you the number of valence electrons. The lone pairs belong to that atom. So the oxygen here owns these lone pairs. And the bond pairs are equally divided between the bonding electrons. So for example, in water, this oxygen has 1, 2, 3, 4, 5, 6 electrons. Gets 1 electron from each bond for formal charge. So 6 electrons in the Lewis structure. It's in column 6, so it has 6 valence electrons to begin with, and so 6 minus 6 means that this has 0. Same deal here with the hydrogens. Hydrogens in the first column, it has 1 valence electron. It has half of 1 bond, so it has 1 valence electron here. So 1 minus 1 gives us 0, and of course this hydrogen's the same. So 0, 0, 0 sums to 0, as it has to. Well, let's look at a couple of, assigning a couple of similar ones of these. So for neutral molecules, the sum of the formal charges must equal 0. So for something like ozone, and here I've drawn out one of the 2 resonance structures, and valence electron for the atom. This comes from the periodic table. Oxygen is from the 6th main column of the main group, and so 6 and 6 and 6 for all the oxygen atoms, for any oxygen atom really. And then how many are assigned in the Lewis structure. So this one has 1, 2, 3, 4, 5, 6 in the Lewis structure. This one here in the middle has 1, 2, 3, 4, 5. So I'm counting the bonds and then adding each electron from the lone pair. 1, 2, 3, 4, 5. And then this oxygen over here has 1, 2, 3, 4, 5, 6. And then half the bond is 7. So now we do subtraction. 6 minus 6 means that this oxygen in this particular structure has no charge. This oxygen here in the middle, 6 minus 5, has a positive charge, and the oxygen on the right-hand side, 6 minus 7, has a negative charge. All right, very closely related ion, NO2 minus. So for NO2 minus here, oxygens, both the oxygens are in column 6, and so column 6 means they have 6 valence electrons to start with. Nitrogen here in the middle, nitrogen's from the 5th column, and so has 5 valence electrons. Then how many is assigned in the Lewis structure? Well, this leftmost oxygen here, 1, 2, 3, 4, 5, 6, looks just like it did in ozone. But actually, this guy also does. 1, 2, 3, 4, 5, 6, 7, looks just like ozone. But now we have a nitrogen here in the middle. The nitrogen has 1, 2, 3, 4, 5. Let's do this simple math now. 6 minus 6 is 0, 5 minus 5 is 0, and 6 minus 7 is minus 1. So notice what changed between the two. Here, when we had an oxygen, it was when we had an oxygen, it was 6 minus 5, so we had a plus 1 for ozone, and so the whole thing ended up being neutral. Here, our formal charge is 0 plus 0 minus 1, so we get a minus 1 overall, and that's what we need to get because this has a minus 1 charge. All right, well, you should know that both of those, we only showed a single Lewis structure. We could have drawn the other resonance structure. I could have drawn the double bond on the right-hand side. In either of these, I could have drawn the double bond on the right-hand side rather than the left-hand side. So let's first review really quickly something that has equivalent resonance structures. And that would be carbonate here. So for carbonate, we could have, it needs to have 2 single bonds to carbon and 1 double bond. But that double bond could be on the left, it could be to the bottom oxygen, or it could be to the oxygen on the right. So there's 1, 2, 3 total resonance structures for carbonate. No single resonance structure accurately describes the carbonate. The actual structure is a combination of these three. All right, well, now let's look at something where we have inequivalent resonance structures. And first, let's look at this one for the equivalent, so I can show you the equivalence. So any of these, I would describe the carbon as having one double bond and two single bonds. One double bond, two single bonds, one double bond, two single bonds. So if I were to use just language to say connectivity here, these would all have the same sort of connectivity. But check out what we can do here with CO2. So this resonance structure has, the carbon has a double bond and another double bond. It has two double bonds. But this other resonance structure that I can draw has a triple bond and a single bond. So the language here is totally different. Double double, triple single. And so that means these are inequivalent resonance structures. Okay, both of these will contribute to the molecule, but they're inequivalent. And when they're inequivalent, one is actually a better description of the molecule than the other individual resonance structure. So this is the one that we're used to, carbon with double bonded oxygens on both sides. But why is this one better? Well, it's better because of Pauling's electronegativity principle explains to us it's better because this has no charge in it, 0, 0, 0, whereas this other Lewis structure here has +1, 0, and -1. So we want to avoid charges if we can. So this makes this a better single Lewis structure to describe CO2. Well, here's one that's maybe even more obvious. So let's use the language again. So oxygen single bond carbon, carbon triple bond nitrogen, oxygen double bond carbon, carbon double bond nitrogen, oxygen triple bond carbon, carbon single bond nitrogen. So these are definitely all inequivalent. So now that we've convinced ourselves that they're inequivalent, which one is the best representation? If we had to pick only one to represent the molecule, which one would be the best? Well, I can very easily tell you which one would be the worst. It would be C. C is the worst because Pauling suggests that electrons will be distributed to the lowest charges on each atom. And we've generated a big 2- charge here, so this is definitely the worst. We have to think a little bit more what's better between A and B. So then the question becomes is if we have to set a negative charge on either oxygen or nitrogen, which atom would be better able to handle it? It would definitely be oxygen because of electronegativity. Oxygen is better at handling negative charge, and so A is a little bit better than B. And C is much worse than either. A is the best here. And here's a little bit more data on that just to let you know. So the two resonance forms of ozone are degenerate, meaning they're 50-50 in the contribution. In other cases, resonance structures are non-degenerate, non-equivalent. For example, the cyanate ion that we saw on the previous slide. In one such example, here's the two better resonance structures, having a triple bond between carbon and nitrogen and having the double bonds on each. So we're not considering here the worst structure, just trying to decide between the two better ones. And we've used here computational chemistry to look at this. And if we take the molecule, there's one and only one molecular ion that we're looking at here, and you calculate the charges, well, you get some negative charge on the nitrogen, some negative charge on the oxygen, and some positive charge on the carbon. Relative contributions of the resonance forms can be qualitatively established based on electronegativity. In this case, the structure has slightly greater contribution of the resonance form with a negative charge on oxygen. And how do I tell that? The negative charge on oxygen in this calculated structure is a little bit bigger. Okay, minus 0.95 versus minus 0.89. And so these aren't quite 50-50. These are something like, I don't know, maybe maybe 60% this structure, plus 35% this structure, and then another 5 from the horrible structure here. So all good Lewis structures contribute to the actual structure of the molecular ion, but the ones that are more stable contribute more. So again, say if we said this was 60, 35, and 5 would be maybe one good way to cut this up.